morning Year 10. Welcome to your physics lesson. So this time last week we were having a look at atoms and isotopes. Underneath the title here you can see there are three diagrams of a nuclear atom. We've got protons, green, neutrons, red, and electrons whizzing around the outside. Now I like this diagram. I like these diagrams, I should say, because the electrons are a bit of a blur. That's because really when we're looking at isotopes and atoms, we're only concentrating on the nucleus. The nucleus is where all the interesting things happen. Okay, this topic is called nuclear radiation because we're focusing on the nucleus. We don't really care about the electrons. A few of you in your questions last week got hung up a bit about the electrons. Just ignore electrons unless you're talking about ions in chemistry. In physics, we never really talk about the electrons. So unless they ask you a question which has the word electron in it, you're not going to use the word electrons. So here you can see we've got three types of a carbon atom: carbon 12, carbon 13 and carbon 14. Do you remember that the number at the end tells us how many neutrons and protons there are? Look at the nucleuses for these atoms. You'll notice there's always 6 green dots. 6 in the 12, 6 in the 13 and 6 in the 14. The thing that is different about the isotopes is they have different numbers of neutrons, and that is what can make atoms unstable. And when atoms are unstable, they become radioactive and decay. And today we're going to have a little look at something called background radiation and find out where it comes from, how much there is, and whether or not we should be concerned about background radiation. So, by the end of this lesson, we should know that background radiation is all around us all the time, and it comes from natural sources such as rocks and cosmic rays from space, man-made sources such as fallout from nuclear weapons testing, nuclear accidents, and even medical investigations. And the level of background radiation and radiation dose may be affected by your occupation and or location, where you live, where you work. So the title for this work today is background radiation. We need to know what background radiation is and where it comes from. By the end of this lesson, you should be able to answer this 6-mark question. Explain what is background radiation and why it is different in different parts of Britain. To get there, we're going to gather information this lesson to help us answer this past paper question. So, radiation is everywhere. We can't taste it, we can't smell it, we can't feel it. We can only detect it with radiation detectors such as a Geiger counter. Now, if you've ever watched any news article about radioactive disasters or any films involving radioactive disasters, you'll know the Geiger counter by its clicking sound. And every time we hear some radiation, it clicks. So where is this all coming from? This sea of radiation that we live in. It's from the rocks, our bodies, plants, radioactive elements, inhaled radon and cosmic rays. The average background radiation per person is 2.6 millisieverts per year. This varies widely depending on where you live, your occupation, your health and your lifestyle. Background radiation. Most background radiation is natural. It's part of nature. It has always been here. People have always lived with it. Write these little sentences down, and then we're going to write a list of the radiation that forms background radiation as we go along. So write this couple of sentences down. Most background radiation is natural. It is part of nature. It has always been here. People have always lived with it. The first place that radiation can come from, background radiation can come from, is space. From the sun and from cosmic rays deep in space. Luckily, we've got our atmosphere around the Earth, and the atmosphere shields us from the radiation coming in from the sun and the space. But if you've got less of the atmosphere above you, you're going to get a higher dose. So if you live at the top of a mountain, go skiing a lot, or spend most of your time in an aeroplane as an air hostess or a pilot, you're going to get a higher dose. Again, thinking about where you live, how high above sea level that you live. Now here are some locations in America. So at sea level, if you lived at sea level, you would on average get a dose of about 0.22 millisieverts a year from just living at sea level. If you live in Death Valley, that's below sea level, so you get even lower dose. As you climb up the hills to get to the top, for example, of Leadville, which is high up in some Rocky Mountains, then you could get a dose just from living there of 1.2 millisieverts per year. Okay, so going up in height by 200 feet in altitude increases your dose by about 0.01 millisieverts per year. People have always lived with it. It's natural. Nobody's really concerned. However, it's a fact. If you live at a higher place, you'll get a higher background radiation. How high is Matlock? If you do Duke of Edinburgh, you might know. Another place where radiation comes from is the Earth, the rocks. So rocks like uranium are radioactive. So's coal and other material that we use for building, like granite. The natural radiation from the granite in Grand Central Station in America, New York, train station, is higher than you're allowed in a nuclear power plant. So if you go to New York Grand Central Station, you'll see that it's a beautiful building and it's made practically entirely out of granite. And this granite is giving off background radiation. And if you stood there with a Geiger counter, you'd be able to measure that background radiation. Another place where radiation is coming from is radon gas. Now that's coming from a rock inside the Earth that is decaying, and then the gas comes out of the Earth. So look here, we've got a house here on top of some rock, and there you can see the gas is seeping out. Now look, usually radon escapes into the air into just very small amounts of it and doesn't hurt us. It goes into the air, disappears. However, sometimes radon can get trapped in buildings and then it can't escape, and then there can be more radiation than is healthy for us. In Derbyshire, we live in an area where radon gas comes out of the rocks in the Earth. And if you live in a radon area, you might have a radon detector in your cellar. You might have people who come round and advise you and tell you to put more ventilation in your cellar to lower the dose of the amount of radon that's gathering there. Radiation comes from within our own bodies. We are made up of elements, and some of these elements are isotopes, and these isotopes decay. In fact, carbon 14 is in our bodies, and we breathe it in through we eat carbon based food, and then we breathe out carbon dioxide, and so the amount of carbon 14 in our bodies is constant. When we die, we stop eating and taking carbon in, and we stop breathing it out as carbon dioxide, and so we can use carbon 14, the isotope of carbon 14, to date objects. So archaeologists use carbon-14 in finding out how old objects are. So our bodies have this carbon-14 in and other isotopes, and we're giving off radiation, but we shouldn't really be worried about other people and giving us a radiation dose from other people, because it is very, very small. There we can see some of the other isotopes. Potassium coming from bananas, plants, that's a piece of broccoli, and milk. Look at the radioactive elements in our bodies. If this pie chart showed the 100% of the radioactive elements in our bodies, you find out that the majority of it was potassium-40. A little bit of lead-210, carbon-14 that I was talking about earlier, and others. However, this is not all the elements in our body. All the elements in our body are not radioactive, only a very, very, very small percent. Finally, we've got man-made background radiation. That can come from X-rays, medical investigations, old-fashioned televisions, smoke detectors, nuclear fuel, weapons fallout. All of these things are man-made sources of radiation. Here we've got a list of all the different types of sources of radiation that we've talked about and approximately how much the dose is. Use this slide to make sure you've got all these things written down in your list of sources of background radiation. You don't need to write down the numbers at all. Okay, so if you have a look, normal annual exposure from natural radiation is about 2.2 millisieverts per year. The average person will get 1.3 of that from radon gas, 0.4 of it from themselves. Rocks and soil will make up 0.28 millisieverts of it, and cosmic rays is 0.27. So look at that. If you live in a radon gas area, your dose is going to be higher. If you live in an area with granite, your dose is going to be higher. Different types of rocks. If you spend most of your time in an aeroplane as a jet setter, international rock star, or a pilot, then your dose from cosmic ray is going to be higher. Then let's have a look about man-made radiation. That's about 0.7 millisieverts per year, so it's already less than half of what we'd get from the natural world. Medical procedures. If you have more medical procedures one year than another, you're going to get a bigger dose. The only reason why we have medical procedures is to investigate things that we want to investigate. So there's no problem having more medical procedures. Consumer products, airline flights, watching colour TV, sleeping with another person, if you share a bedroom with somebody. Weapons test fallout, so that's the radiation that comes from the remnants of a radioactive test. Nuclear industry. So things that people are worried about when it comes to radioactivity is usually weapons testing and the nuclear industry. But look how small that dose is there. You get more of a dose from going on an aeroplane from one side of the America to another than you would do from all of the nuclear industry in the world. So we've got all these lists of sources and where they come from.